Dear friends, welcome back. In our previous example problems, there was a mistake, like a small mistake that we have made. So let us solve these example problems again. Right? I'll quickly go through these examples again. First example is, consider a fixed wing UAV flying at an altitude of 5 kilometers with a velocity of 30 meters per second. Find corresponding total pressure measured by the pitot tube. So the information that is given here is, geometric altitude is 5 kilometers. So first we need to find the total pressure measured by the pitot tube. So we have velocity of the flight vehicle as 30 meters per second. So how to find the total pressure? PS at 5 kilometers, that is the static pressure at 5 kilometers, plus half density at 5 kilometers and the corresponding velocity square. Right? So this is the dynamic pressure part, and this is the static pressure. So at 5 kilometers we know the aircraft is flying in the gradient layer. You need to find the corresponding static pressure at 5 kilometers by using gradient layer equations. So what we have is P at 5 kilometers by P at sea level, or P at sea level is equals to T at 5 kilometers divided by T at sea level minus G naught by AR. Right? This is the relationship between pressure and temperature at different altitudes, where G naught is 9.81 meter per second square and A is minus 6.5 into 10 power minus 3 Kelvin per meter, and R is 287 joule per kg Kelvin. Right? Now if I want to find pressure, static pressure at 5 kilometers, I need to know what is the corresponding temperature at 5 kilometers. Since we know the static pressure or static pressure at sea level and the corresponding temperature at sea level. So if I can find out T5, I will be able to calculate P5, P at 5 kilometers. So to find out T5, what I use is the definition of lapse rate. This implies T2 minus T1 is equals to A into H2 minus H1. So first we need to convert this geometric altitude to the geopotential altitude here. So H is equals to R into Hg by R plus Hg. So this R is the radius of Earth, let us say small r, where R is equals to 6,400 kilometers. Right? This is equals to 6,400 kilometers by 5, 64 not 5. So this is approximately equal to 4.9961 kilometers. See, the difference is very, very less. At lower altitudes, the geopotential and geometric altitudes are almost same. Right? And now, what is temperature? T2, T at 5 kilometers is equals to T at sea level plus A into delta H, which is T at sea level is 288.16 Kelvin minus 0.0065 into 4.9961 into 10 to the power of minus 3. Right? So this equals to, that implies T at 5 kilometers is equals to 255.685 Okay. That. Now, P at 5 kilometers is equals to P at sea level. Otherwise, we know what is P at sea level, 1.01325 into 10 to the power of 5 Pascal into 255.685 Kelvin by 288.16 Kelvin raised to the power of minus 9.81 divided by minus 0.000065 into 287. Right. What you get from here is 54.08 kilopascals. Correct? So now, to find out the total pressure at that particular altitude, I need to find corresponding density at that particular altitude, right? Total pressure at that particular altitude, or 5 kilometers, is equals to static pressure at 5 kilometers plus half. What will be the density at that particular altitude? P is equals to rho RT, or you can use the gradient layer equation, or P at 5 kilometers is equals to density at 5 kilometers R into temperature at 5 kilometers. You know these values, right? You know P at 5 kilometers is 54.08 kilopascals. You know density at that altitude. I'm sorry, we have to find the density at that altitude. You know what is R, and T5 is derived here, 255 points. So using this, what you can use it, pressure at 5 kilometers divided by R into T at 5 kilometers into velocity square, V infinity square, where density at 5 kilometers is equals to T at 5 kilometers divided by R into T at 5 kilometers, using equation of state. This implies, what is P at 5 kilometers is 54.08 kilopascals into 10 power 3 plus half into 54.08 into 10 power 3 divided by 287, 255.685 into 30 square. So the aircraft is moving at 30 meters per second. So the corresponding velocity square is 900. What you have from here is 544.11.638 Pascal. Now, let's look at example 2. Determine the cruise velocity of a wing-alone UAV flying at an altitude of 10 kilometers. The pitot tube measures a total pressure of 26.723 kilopascals. What will be the velocity of flight? So we need to determine the velocity of flight at 10 kilometers altitude. So Hg is 10 kilometers, and what we have is total pressure at 10 kilometers altitude is 26.723 kilopascal, right? Kilopascal. Okay. Now, if I need to find the velocity, what I need is a differential pressure, right? So P naught is equals to Ps plus half rho V square, where S stands for static pressure here. So to find the velocity at that particular altitude, you need to know the differential pressure, which is total pressure minus static pressure, and the corresponding density at that particular altitude. Now we need to find what is this static pressure at 5 kilometers. Since we know P naught at 5 kilometers and density, 10 kilometers here. Please make a correction, it's 10 kilometers, density at 10 kilometers. Okay. Now first we need to convert Hg to H, which is Hg into R by R plus Hg, which is equals to 6400 by 6410, which is 9.984 kilometers. Right. Now the corresponding temperature at that altitude is? Why? Because if I want to know what is the static pressure at 10 kilometers, in the previous example we witnessed we need to find temperature at that particular altitude, right? So T at 5 kilometers from the definition of lapse rate is T at sea level. 10 kilometers is T at sea level plus lapse rate times delta H. This equals to 288.16 minus 0.0065 is a slope of this gradient layer, first gradient layer, and the change in the altitude is geopotential altitude 9.984 into 10 power 3 meters. So temperature at 10 kilometer altitude is equals to 223.26 Kelvin. Now pressure at 10 kilometers altitude is, by using gradient layer equation, we have pressure at sea level and temperature at 10 kilometers altitude, temperature at sea level, raised to the power of minus G naught by A R. Right. So by 101.325 kilopascal, to 23.26 divided by 288.16 raised to the power of 9.81 divided by minus 0.065 into 287. What I have from here is 101.325 into 10 power 3. This is the atmospheric pressure at sea level, 0.2619. So this equals to 26.537 kilo pascal. So pressure, static pressure at 10 kilometers is 26.537 kilopascals. So to find the velocity, we need density as well, density at that particular altitude. So by using equation of state, P at 10 kilometers is equals to rho at 10 kilometers, R into T at 10 kilometers. So what we have here is density at 10 kilometers is equals to, what is P at 10 kilometers? It's 26.537 into 10 power 3 divided by 287 into 223.26 Kelvin. So this implies density at 10 kilometers is 0.414 kg per meter cube. So density at sea level is 1.225 kg per meter cube, right? 1.225 kg per meter cube. See, the density is decreased by more than half. Now the velocity of flight at 10 kilometers, where the static pressure, the total pressure measured by pitot tube is 26.723 kilopascals minus static pressure at that altitude is 26.537 kilopascals divided by density at that particular altitude. Which is approximately 30 meters per second. So this is the velocity at which this wing alone UAV is flying, right, at 10 kilometers altitude. So let's revisit example number 3. Consider the differential pressure measured by the pressure sensor of a UAV cruising at 30 meters per second is 0.4 kilopascals. Find the corresponding altitude of flight. So what we have here is P0 minus PS at a particular altitude h is 409.05 Pascal, and we know the corresponding velocity of flight is 30 meters per second. So by some means you got to know, some other instruments you got to know what is the velocity of this flight, right? Now we have to find the corresponding altitude of this flight. So from the so we know the velocity is root over twice the differential pressure. Velocity at that particular altitude, say h, is the differential twice the differential pressure at that particular altitude divided by density of at that particular altitude. The whole thing is under root. Yeah. Since we know velocity and the differential pressure, we can find the density at that particular altitude. In that case, density at that at h is equals to velocity square minus 1 into 2 times P0 minus PS at that particular altitude. Okay. Now density at height h is equals to 2 times 409.05 pascals divided by this equals to 0.909 kg per meter cube. So this is density at h, right? Now since most of these flights are in gradient layer, we assume that for this current course we assume that the flight happens in the gradient layer. So for this particular density at h and density at sea level, we can relate this to the corresponding temperature, because if I need to find the altitude, what I need to know? See, the only way is like I have the definition of lapse rate where I have dt by dh. If I know this dt, I can find this dh, since the slope for this first layer is constant, right? For the slope for any of these gradient layers is constant, right? Now this is a t at that particular altitude by t at sea level, raise minus g0 by ar minus 1. Okay. This equals to 0.909 divided by 1.225 is equals to temperature at that particular altitude by sea level temperature 6 Kelvin. This is minus 9.81 by minus 0.0065 into 287 minus. This implies TH, T at that particular altitude is 268.624 Kelvin. Now I know what is the temperature at this particular altitude h, right, by using definition of lapse rate. del A is equals to dt by dh, and what we need is dh is equals to dt by A. dh is h, because with reference to sea level I can write dh as h here. h2 minus h1 is equals to h minus 0, that is equals to t at altitude minus t at sea level divided by A. This implies h is equals to 268.624 Kelvin. 64 minus 288.16 is the sea level temperature divided by minus 6.5 into 10 power minus 3 Kelvin per meter. This equals to 3.005 kilometers. Is what you have, the h here is 3.005 kilometers. Now the corresponding geometric altitude is h into radius of earth, right, small r, divided by r minus h. This equals to 6400 into 3.005 divided by 6400 minus 3.005. Hg is 3.0064 kilometers. So you're approximately flying at 3006 meters, right? So the altitude of flight is approximately 3 kilometers. You can consider. So the difference between geometric and geopotential altitude is very, very less here. Let's solve this final example again. The static pressure sensor of a UAV measures a pressure of, that means this is the static pressure that is measured by this UAV, which is approximately 53.75 kilopascals. So we need to find the corresponding altitude of flight of this UAV, right? So it's pretty straightforward, right? So, but this is in fact the practical way to find out the altitude by using the static pressure sensor, right? You have the static pressure sensor, and that particular sensor measures the static pressure at the particular altitude. Now you need to find out the corresponding altitude of flight, right? So what I have is PS static pressure at h is equals to 53.75 into 10 power 3 Pascal, right? So what I need to find is the altitude. So if I have to find the altitude, I need to know what is the corresponding temperature at that altitude. So from the gradient layer equations, P at the altitude divided by P at sea level, static pressure at that altitude divided by static pressure at sea level is equals to temperature at that altitude by temperature at the sea level raised to the power of minus G naught by yeah. Right. So this implies what I have is TH by T at sea level is equals to P at altitude and static pressure at sea level raised to the power of minus 1 by G naught or minus AR by G naught. This implies the temperature at that particular altitude is static pressure at that altitude. It's the ratio of static pressure at that altitude and sea level static pressure raised to the power of minus AR by G naught. So the temperature at this altitude is equals to 288.16 Kelvin times temperature pressure at that altitude 53.75 divided by 101.325. So both are in kilopascal. 1 by 5.25, right. So this equals to temperature at that altitude is equals to, so 255.378 kilopascal, sorry, Kelvin. So you have the temperature. Now by using definition of lapse rate, delta H is equals to T2 minus T1 or TH minus T at sea level divided by minus A. This equals 255.378 minus 288.16 divided by minus 0.0065. This implies H is equals to 5.043 kilometers, right. So we have geometric altitude. Now convert this to corresponding geopotential altitude, right. R into H divided by R minus H. This is 6400, 5.043 divided by 6400 minus 5.043. Okay. Equal to 5.0469 kilometers. This is the altitude at which this UAV is flying, right, when it is measuring static pressure of 53.75 kilopascals. Now what is the difference between geometric and geopotential altitude? It's 5.0469 minus 5.043. This is hardly 3.9 meters. So this is the difference between geometric and geopotential altitude, right. Now here we have static pressure, right. So let us look at some of the sensors that we have right now that can measure the total pressure and static pressure. Let us look at this pitot-static tube. See, the holes that you can see on this periphery are meant for static pressure. Yeah, and you can see one hole which is along the longitudinal axis of this tube, that is meant for total pressure, right. So these holes are along the circumference of this outer tube, right. You can consider there are two coaxial tubes, one with a closed mouth, the other with the open mouth here, right. So this particular outlet is for static pressure, and the one which is straight here along with this tube, along the longitudinal axis of this tube, is for total pressure. So let us look at this pitot-static tube and the corresponding pitot-static sensor, pressure sensor. It's a differential pressure sensor, right. So the bottom inlet is meant for static pressure, to measure the static pressure, and the top one is for the total pressure. So the output from here, what you get is a differential pressure. This is the differential pressure sensor. You can see the scale of this sensor is about a centimeter long, right, less than a centimeter, and the total sensor size is about 2 centimeters, right. This is the differential pressure sensor, and the size of this sensor is about 2 centimeters here, including the PCB, which helps you to acquire the data, right. And it weighs hardly 15 grams, right. And we have another sort of sensor that is mounted on this Navio 2 autopilot. See, what you have here is a static pressure sensor. So for this static pressure sensor, you will not be able to connect any tube from the static port. Rather, wherever you mount this, you need to allow this particular board to interact with the atmosphere, right? You can't make it isolated system. You can't keep this isolated from the atmosphere. All you need to do is make a small slit so that the air in that cabin interacts with the surrounding atmosphere, right?